Hello friends. In my lecture series on thermal physics, I have started with discussion on heat engines. To discuss heat engines, we have to discuss heat cycles. I have discussed Carnot cycle in great detail, and now I am on discussion of the Stirling cycle. So resuming my discussion of Stirling cycle, just let me briefly tell you about the various processes that make up the Stirling cycle. The Stirling cycle, as you can see from the PV diagram, has 4 processes. Process which takes the gas from state 1 to state 2, state 2 to state 3, state 3 to state 4, state 4 to state 1. Because every cycle has to be cyclic in nature. It is by the name it is a cycle, so it has to come back to its initial position. So process 1 to 2 represents the isothermal heat addition process, in which the volume of the system increases and the pressure decreases. Process 2 to 3 represents the isochoric heat removal process, in which the temperature and the pressure are both decreasing, but the volume is constant. That is, no work is going to be done when the system is going from state 2 to state 3. Process 3 to 4 is representing the isothermal heat removal process, in which the volume of the system is decreasing and the pressure is increasing. It is occurring at constant temperature. Process 4 to 1 is representing the isochoric heat addition process, in which the temperature is also increasing and the pressure is also increasing, but the volume is a constant. Therefore, from 4 to 1, again the work done is going to be 0. So you can clearly see that the work done is only from state 1 to state 2 and from state 3 to state 4. There is going to be no work done from state 2 to state 3 and from state 4 to state 1. This is very important concept which was used in the Stirling cycle. Now, Stirling cycle, as you can see, I have tabulated all the major results which are happening in all the processes in the Stirling cycle. From process 1 to 2, the change in internal energy is 0. The heat interaction is RT1 log of V2 by V1. The work done is also RT1 log of V2 by V1, because in an isothermal process, W is equal to Q. In the process 2 to 3, the change in internal energy is CV T2 minus T3. Heat interaction is CV T3 minus T2, and the work done is 0. From process 3 to 4, the change in internal energy is 0. The heat interaction is RT2 log V2 by V3. Work is RT2 log V2 by V3. And process 4 to 1, the change in internal energy is CV T1 minus T2. Heat interaction is CV T1 minus T2, and the work is 0. This has to be 0 because this is an isochoric process. Now, as I mentioned in my previous lecture also, that every cycle is defined by its efficiency. How good the cycle is determined by the efficiency of the cycle. So let us now calculate the efficiency of a Stirling cycle. By definition, eta is the ratio of work output to the heat input. Work output is RT1 log V2 by V1 plus CV T1 minus T4 minus CV T2 minus T3 plus RT3 log of V3 by V4. The heat input is RT1 log of V2 by V1 plus CV T1 minus T4. To find out the efficiency, we have to divide the work output by the heat input. So let us divide them. After dividing them, we get an expression in which if we use the relation that the heat rejected in process 2 to 3 is used for the heat addition in process 4 to 1, the term CvT2 minus T3 will get cancelled by CvT1 minus T4. Also remember, V3 by V4 is equal to V2 by V1. The ratio of the volumes is the same. We get eta is equal to 1 minus T3 by T1. This is qualitatively similar to the efficiency of a Carnot cycle. Next, let us discuss Otto cycle. We have discussed Carnot cycle, we have discussed Stirling cycle. The next cycle which I would like to take up is Otto cycle. Again, this is a very important cycle. You can see the schematic, the PV diagram of the Otto cycle, again drawn on the PV curve. In 1876, Nicholas Otto invented the Otto cycle. The Otto cycle is most commonly used in SI engines, that is petrol engines, for their proper operation. Almost all the latest gasoline engines work on the principle of Otto cycle. This is showing the essential components of the Otto cycle. As you can see, it is a 4-stroke cycle. This cycle completes a working stroke in 4 steps. That is, it works between 2 isocores and 2 adiabates. The engine under the hood of a car bears a slight similarity to Otto cycle. It means an engine which is following the Otto cycle. The cycle begins at A. From A to B, the piston recedes and a valve is open, so that a mixture of air and petrol, that is the gasoline, is drawn in at constant atmospheric pressure. Now what happens at B? The valve is closed, and from B to C, a fixed mass of gas is compressed adiabatically, the temperature being a few hundred kelvins. At C, what happens is this, that maximum compression takes place and a spark is struck, ignition spark. The mixture is ignited and the temperature of the gas suddenly instantaneously shoots up to perhaps 2000 Kelvin at constant volume. The gas, now having reached D, expands adiabatically to E, doing work, and the temperature drops somewhat. At E, the second valve opens now. The gas is expelled, exhaust gas. The pressure drops to atmospheric pressure and the temperature drops to its original value. We are now at F. The piston pushes the remaining gas out and we end up at G. The cycle starts anew, because for any engine to be efficient, the engine has to operate in a cycle. Next, we will calculate the efficiency of an Otto cycle. Q1, that is the heat absorbed, is given by Cv Td minus Tc, and Q2, that is the heat rejected, is given by Cv Te minus Tb. By definition, eta is work output over heat absorbed. Substituting the values of work done and heat absorbed, we will be able to get the efficiency of an Otto cycle. So eta is equal to 1 minus Q2 by Q1 is equal to 1 minus Te minus Tb over Tb minus Tc. Now we will use the relation Tv gamma minus 1 is equal to constant. With substituting this in the above expression, we get eta is equal to 1 minus Tb by Tc. So this is a brief discussion about Otto cycle, and I hope you have understood and the concepts of heat engines and what is a heat engine all about. Next, I would like to discuss a very important topic in thermal physics, real gases. Ideal gases has been discussed in a number of places at school level, but real gases have not been touched in so much of depth. So what I would now like is to tell you what are real gases and what is the important experiments that gave us all the information about real gases. So first of all, what is a real gas? A real gas is a gas that does not behave according to the assumptions of the kinetic molecular theory. It directly implies that ideal gas follows the assumptions of kinetic molecular theory. Now just let me briefly tell you that you cannot say that oxygen is an ideal gas and nitrogen is a real gas. All gases can behave in an ideal manner. The same gases can behave as real gases depending upon the temperature and pressure at which those gases are being studied or are being observed. Generally, a departure from ideal behavior is seen at low temperatures and high pressures. The contents of my lectures have been designed in the following manner. I will briefly discuss about the differences between ideal gases and real gases to begin with. Then I will move on to some very important experiments in real gases, the Andrews experiment and the Joule-Thomson's experiment. I will also be deriving the very famous van der Waals equation. So let me first of all tell you about the differences between ideal gas and real gases. In ideal gases, molecules are considered to be point masses, whereas in real gases, the molecules have finite volume. It means they have some size. In ideal gases, the intermolecular forces of attraction are totally absent. In real gases, the intermolecular forces are present. The internal energy of an ideal gas is a function of temperature alone. This is a very, very important difference between ideal gases and real gases. In real gases, the internal energy is a function of temperature and volume both. Ideal gases follow the kinetic theory and the elastic collision between molecules of the ideal gas occur. Real gases do not follow the kinetic theory and inelastic collisions of the molecules occur. The equation of state for an ideal gas is PV equal to nRT. There can be different real gases depending upon the equation of state we are considering. We can have the van der Waals equation, we can have the de Trisi equation, we can have the Berthelot equation. These three equations are named after the scientists who empirically derived these equations. Van der Waals equation is given by van der Waals. The de Trisi's equation of state is given by de Trisi. The Berthelot equation of state is given by Berthelot. And you can see the simplest of equation of states for a real gas is given by van der Waals equation, which states that P plus A by V square into V minus B is equal to RT for 1 mole of a gas. We will be concentrating on van der Waals equation of state in this series. To find out more information or more insight into real gases, where many experiments were performed. The most important experiment is the Andrews experiment. I will show you the apparatus in a few moments. Just let me tell you what is the principle of this experiment. The principle of this experiment is that the volume of fixed mass of gas at various pressures and at a given constant temperatures is measured. Isotherms are drawn. Various isotherms for different fixed temperatures is obtained and the deviation from ideal gas law can be studied. This is the apparatus of Andrews experiment. This is the explanation of apparatus of Andrews experiment. I will just show you the apparatus in a few moments. It consists of two similar glass tubes A and B having capillary tubes C and C' at the top. In tube A, pure dry air is passed for a long time and the ends are sealed. In tube B, the experimental gas CO2 is passed for a long time and again the ends are sealed. The lower ends of both the tubes are immersed in mercury. Small pellets of mercury are drawn in both the tubes by alternately heating and cooling the tubes. Both the tubes are fixed in an H-shaped copper vessel having stoppers S and S'. The vessel is filled with water and by screwing in the plunger, the water is compressed and pressure up to 400 atmosphere can be applied. So this is what we are doing. At constant temperature, we are going to change the pressure and measure the volume. Just let me move on, show you first of all the apparatus. This apparatus I was talking of. So as you can see, you have two capillary tubes fixed at the top which has glass tops. S and S' are two screws. We can apply pressure via them. You can see the mercury also, the water also. So this is as far as the apparatus is considered. The tube shown on the left has the test gas. Tube shown on the right has carbon dioxide gas. Andrews experiment was performed for carbon dioxide gas. Very, very important. This is the isotherms that Andrew obtained for carbon dioxide. He drew the isotherms at various temperatures. By isotherms, we mean the PV curves obtained at constant temperatures. And you can see they are following different patterns. The isotherm at the top is simply part of a hyperbolic, and then we have different shapes. You have horizontal portion. The explanation of each is going to be discussed in a few moments. Since pressure on A and B are same, from volume of air in A, the pressure of CO2 can be calculated. The volume of B can be read directly. The temperature of CO2 is maintained at specific temperatures. Now let me discuss the results of Andrews experiment. This is a very, very important experiment, and I will tell you from this experiment, for the first time it was seen why certain gases can be liquefied and why certain gases cannot be liquefied even though you apply a massive pressure on those gases. So isotherms were drawn at various temperatures on a PV curve. At 13.1 degrees Celsius, AB represents the gaseous state of CO2 up to point P and obeys Boyle's law. From B to C, it shows an enormous decrease in volume with slight increase in pressure. At 31.1 degrees Celsius, horizontal portion vanishes. It is a very important isotherm. It means the isotherm at 31.1 degrees is very, very important, because in this isotherm, the horizontal portion which is occurring in the lower curves totally vanishes. This is called the critical isotherm for carbon dioxide, because something different is happening above it and something different is happening below it. So this is the changeover point. Above this temperature, the gas cannot be liquefied. It means above this temperature, CO2 is acting as an ideal gas, and below this temperature, CO2 is acting as a real gas. At 35.5 degrees Celsius and 48.1 degrees Celsius, no horizontal portion is seen, gas cannot be liquefied, and Boyle's law is obtained. It means at 35.5 and 48.1, CO2 is again acting as an ideal gas. BC represents the change of CO2 from gaseous to liquid state. At point C, the gas has been completely liquefied, and the portion CD represents the liquid state of CO2. at 21.5 degrees Celsius, the curve is similar to the above, but with one difference, the horizontal portion Fg is decreasing. So, what are the experimental findings that Andrew made it known? Andrew found that the liquefaction of CO2 occurs only below 31.1 degrees Celsius, called the critical temperature. There is no physical distinction between liquid and gas on the horizontal portion of the isotherm. The gas behaves almost as perfect above the critical temperature and cannot be liquefied at any pressure. The density of liquid and vapor becomes equal at the critical point. Andrew defined certain very important parameters in thermal physics. The critical point. It is the point on the isotherm at which the gas can be liquefied. The critical isothermal. Isothermal corresponding to critical temperature. Critical temperature Tc. The highest temperature at which a gas can be liquefied by the increase of pressure alone. Critical pressure Pc, the pressure applied to a gas at its critical temperature so that it gets liquefied. Critical volume Vc, the particular volume of gas at critical pressure and critical volume. So, I hope you have understood what is the Andrews experiment, what is the importance of Andrews experiment. Andrews experiment made it known to us for the first time why certain gases are being liquefied and why those gases are not being liquefied at certain temperatures and certain pressures. Continuing with the series, I will in future classes calculate the critical temperature, critical pressure, critical volume in detail for a van der Waals gas as well as some other real gases. So, I hope you have understood this particular concept of real gases. Thank you.